Alright, good evening and welcome. This is Obi-Wan Pez for N Simplex Pachinko. And tonight we are going to get into some trigonometry that I do on a regular basis for my Trig class, and then also expand it just a little bit further due to the fact that I proved a formula which was, it's been well known for like hundreds of years anyway. But it was something that isn't readily available, so I didn't find the proof for it anywhere, and so I was just like, all right, well, let's get it done, see if I can do it, and then give it to my class. And when I did it, it turned out to be super simple. So I thought I'd just show it off anyway to be like, well, here you go. As always, after this first little interlude here, we'll open things up and anybody can ask any questions you like. We're coming up on my school's spring break, so I will be able to stream a bit more often next week, I think. And I'm also planning on doing some streams for the Elite Dangerous Alpha that just got released for Odyssey. Let me maybe reword that. The Elite Dangerous Odyssey Alpha release that just came out. Might in fact do some of that tonight if we're kind of all done at the end, just for fun, because why not? I finally was able to figure out how to complete some missions, so about time. All right. So, my intent was to start off with... Yep, there we go. That works too. Alright, to start off with two angles. The first one we are going to call alpha. And the second one, which is completely arbitrarily placed, right? Both of these are any angles on the entire circle, so it does not matter where they go. It's just that these two angles are going to be called alpha and beta, and the angle between them is going to be called alpha minus beta, due to the fact that we're taking the arc of alpha and then chopping out the beta part here. This allows us to come up with a few different formulas. So those of you who have done Trig before, maybe you've seen just the beginning of it, I was doing this today and a couple of days ago in my trigonometry class, so it's about time in the semester for it. Now, for any particular location on the entire circle, you have a right triangle which can be built out for this particular location. And for any circle, I'm going to undo that, hang on. It's a lovely circle. Okay. So for any particular point that is going to be on our circle, this can be a circle of any radius. So we'll label it with R here, with X and Y in these two places. And our angle, theta, is going to be the interior angle here. Now, several relationships exist in this that we're going to be using for tonight. The first of which is our sine function. The sine of theta on this particular triangle is going to be y, that distance y, divided by r, our radius. The cosine of this particular function is, you could either think of it as, again, adjacent over hypotenuse, that stuff you've always learned going way back to your first exposure to geometry, or you could think of the cosine as the complementary sine, or the sine of the complementary angle. So the complementary angle to theta here is going to be, let's see, a rho, I guess? That's kind of weird. It's in the middle of this. Let's call it delta. So the cosine of theta is going to be the same as the sine of delta. When we look at this, this made a rectangle, which got us both our x up here and our y over here. It is a right angle, so this is going to make a nice little rectangle here, split up into two pieces. Each of these triangles should be the same thing, but my drawing is terrible, so excuse me on that. The sine of delta is going to be the opposite, x over the hypotenuse r, which is again what we see for just thinking about the cosine of theta. Everybody's familiar with your old SOHCAHTOA stuff. I'm not going to do that just because it is a bunch of tricks that you just memorize, and anybody who's been on this channel for a while knows that I'm not really big on like things that you memorize. I really want you to learn stuff at a much deeper level. So the sine of any particular curve is going to be its height divided by its radial distance. So we're going to get something like that. And this is true for anywhere on the circle. So even if we drew an angle in the fourth quadrant down here, which was a different angle than the one above, right, this is clearly steeper, totally, we would have a new x value in here. That's a bad place to put it. All right, we got a new x value in here. This would be like x2 here, where you're not going to be able to tell those apart. All right. So we can call that one x1, and we can call this one down here x2. This could then be a y1 here. And y2 there. And one of the important things about this particular angle is going to be that it does have its actual value, its actual measurement is going to be this angle measurement here. However, it's also possible, instead of listing this as tau, instead of just listing this as tau, we could also use the interior angle on this triangle. That's a right angle. This interior angle on this triangle to be called our reference angle. And a reference angle in this particular case could be called tau prime. It's much easier to do trigonometry and calculations and stuff like that on tau prime, and then at the same time remember that you're in the fourth quadrant. So it's an angle that's going to be between 0 and 90. You just have to remind yourself it's in the fourth quadrant. What does that mean? Well, a lot of teachers do that whole like drawing out in quadrant 1. These things are positive and these things are negative. In quadrant 2, these things are positive and these things are negative. Again, you don't need to do that. You don't need any of these tricks or stuff like that. What is it that you're looking for? Well, if you're looking for the sine function is based off of the y values. Where are the y values positive? Up. Where are the y values negative? Down. If you're doing cosine, then you're looking at the horizontal values, your x values. So where are they positive? Everywhere to the right. Where are they negative? Everywhere to the left. So again, you don't need to worry so much about that. And then the secant is based on the cosine values, so it's based on the x values, so that has the same thing. And the cosecant is based on the y values because it's based on the sine. So again, up and down. The tangent and cotangent are the only weird ones. I have shown it before, but might be a good thing to do again. The tangent of theta is equal to y over x. And for anybody who'd noticed, we're also going through not just the point x comma y, where these come from, but also 0 comma 0, the center, the origin. So if we were to write something like y minus 0 over x minus 0, well, that looks familiar, doesn't it? This is just the slope equation for the slope between these 2 points, 0, 0 and xy, 0, 0 and xy. So m here, the tangent of theta, is going to be the slope of the terminal side of an angle. Alright, so again, using tau prime, we can look at our reference angle and figure out some easier stuff with this. So we look at the inside of this triangle. If you want to know what the sine of tau prime is going to be, the sine is based on the y values. The y values are negative, so negative whatever it is over r, negative 3 over 7 or something like that. And similarly for cosine, you're going to be looking at the x value here, x2 divided by r. It's in the positive direction because it's off to the right, and that's going to end up being a nice positive value. Okay. So back to this stuff. If we want to know a better way to get this, right, there is another way to state this. If we get y by itself, then the sine of theta equals y over r is going to yield instead y equals, multiplied by r on both sides, r times the sine of theta. The cosine of theta is equal to x over r, and therefore x can be equal to r cosine theta. All right, based on that, we can come back here and look at alpha and beta. We can do the same things. So here we have a point that is r cosine beta by r sine beta. And again, this is irrespective of where you drew it in the entire circle, it's still going to have these same values. So r is just the radius of the circle. Cosine of beta, beta is whatever angle you drew. Doesn't matter where it is. All right, and then we've also got another point down here, which is at r cosine alpha by r sine alpha. All right, now, what if we take another one of these circles? Oops. Is it gonna go? No. Okay, cool. Apparently I didn't close my shape enough. Or it didn't go all the way around the... Yeah, that's probably it. Yeah. Didn't go around the square that's actually surrounding it. Oh well. Alright, if instead of drawing beta here at whatever angle beta is, we were to take this entire shape, the entire angle that we have, and then just tip it, oops, that way, and then just tip it that way, so that beta is now, instead of off in space, lying flat against the x-axis. Beta now becomes our terminal side. Then the point r cosine beta, r sine beta, is going to be repositioned on top of, well, this is r in the x direction and 0 in the y direction. If we take beta off of our alpha angle, then this is going to end up being somewhere, roughly speaking, over here-ish. And we get another connection point here, intersection point with the units, or with the circle. It's not a unit circle, which is going to be at, again, this angle was now alpha minus beta. So we get r cosine alpha minus beta, parentheses, by r sine, parentheses, alpha minus beta. There's also something rather interesting about these particular... There is something rather interesting about these particular angles, in that if we were to draw the direct line distance between these 2 points, and the direct line distance between these 2 points, then we'll notice that the direct line distance between this point here and this point here could be labeled d for just distance. And the two radii on this circle are going to end up being the same as each other. And also, the radii on this circle are the same as each other and also the radii up above. So we have two sides of the triangles that have been produced here that are going to get us the same thing as each other. Then the exterior angle alpha minus beta, we can look at the interior angle of both of these triangles, and provided I haven't completely messed this up, our angle in here is going to be 360 degrees, or 2 pi radians, minus parentheses alpha minus beta. And it's the same in both triangles. So now we have a side, an angle, and a side, which are corresponding to a side, an angle, and a side up above. These triangles, therefore, are congruent, and therefore the distance between these two things is going to be the same. Also D. Now, you probably could have said, well, yeah, we just took the shape and all we did was tilt it, so therefore we didn't change any measurements about that particular shape. And yeah, you can go that way too. Depends on how pedantic the person who is in charge of your grade is being. In my case, very. Alright, now the distance formula for these, because the distances here and here have to be the same, but because the points are different from each other, we're going to use the distance formula and come up with two different expressions which are going to get us something very nice. So, up top here, when we look for the distance, what we're doing is we're going to draw in a big right triangle and say, okay, what is the horizontal distance dx, or delta x, not dx, delta x versus the vertical distance delta y. You could do the same thing here. We're going to make a delta y here and a delta x here. These are in fact different numbers, but in both cases, d squared, the diagonal, is equal to the sum of the squares of the two sides. Delta x squared plus delta y squared. So again, up above, d squared is going to be equal to the distance between these two things is going to be the difference between their y values. So here, r sine theta, r sine alpha and r sine beta are two y values. So to find the difference between them, that's going to be the delta y. Similarly for delta x, we take our cosine theta and subtract our cosine beta. You could do it in any order you want because this is going to be squared, so the only thing that's going to... nothing's going to change its sign if you reverse their positions and then square them. So d squared from up top is going to be delta x, which is r cosine alpha minus r cosine beta. That's squared. Plus, parentheses, delta y is going to be r sine alpha minus r sine beta squared. And it's also going to be equal to the delta x squared and delta y squared from down below. Delta x squared is going to be r cosine of alpha minus beta minus r parentheses squared plus r sine of alpha minus beta minus 0 squared. That doesn't change a whole lot, but it's still necessary to write it out. At least the first time when you're trying to prove everything. Now, d squared is equal to, here, you've got r squared cosine squared alpha minus 2r squared cosine alpha cosine beta plus r squared cosine squared beta. Now, if you're saying to yourself, now, why did you just do that? We know that whenever you have two things added together and then you're squaring the sum, you're going to end up getting an a squared term, two ab terms, and a b squared term. So now we're on to the second one. So plus, this is now going to be r squared sine squared alpha minus 2 r squared sine alpha sine beta plus r squared sine squared beta. Then we also have this side, which I'm going to just put on the next line, indented. So this is going to be r squared cosine squared alpha minus beta minus 2 r squared cosine of alpha minus beta. Plus r squared. Then the second grouping has a plus r squared sine squared of alpha minus beta. And then we get a minus 0 times r, this other stuff, plus a 0 squared. So the rest of this is just plus 0 if you really want to write it. Most of the time I'm not going to care. Okay, so now we can see that, well, first of all, we don't need the d squareds anymore. So we can get rid of this. It is still equal to that stuff, but it doesn't matter. This is the relationship we want to focus on. So getting the expanded groups of binomials and put them all together in some way, shape, or form, that's going to help. Now, first thing you can do is divide everything by r squared. Because we don't need that. Next thing we can do is look and see that we have a cosine squared of alpha and a sine squared of alpha. We have a cosine squared. Let's get rid of that one. Different color. Cosine squared of beta and a sine squared of beta. You might wonder where this is all coming from. This comes from the basic ideas that we had up here, where we had an x, a y, and an r for our three sides of these triangles that we're building anywhere inside of this circle. So if we have x, y, and r, then we can take the Pythagorean theorem for that. So x squared plus y squared equals r squared. And then once you do that, you can also say, well, y is going to be r sine theta, and x is going to be r cosine theta. So this is r squared cosine squared theta plus r squared sine squared theta equals r squared. So the cosine squared of theta plus the sine squared of theta is equal to 1. This is the basic Pythagorean identity. Anybody who's taking trigonometry, you're going to need to know that one. But in order to minimize the memorization that you have to do, it would be really helpful if you know where it came from. At least practice that a couple of times, see if it works. Should stick. All right, the r squared cosine squared alpha plus r squared sine squared alpha is going to get us a 1. The r squared cosine squared beta plus r squared sine squared beta is going to get us another 1. Again, we're dividing by r squared. And then we have a minus 2. We divided out the r squared. Cosine alpha, cosine beta. And a minus 2 sine alpha, sine beta. Is equal to r squared goes away here. We're just left with the cosine. Nope. Because forgot. Cosine squared of alpha minus beta and sine squared of alpha minus beta are again going to get us another 1. Right. Are going to get us another 1. And the r squared here is going to get us a 1. Then we have a minus 2 r squared. Or now, just minus 2 cosine of alpha minus beta. We have a 2 here, and we have a 2 here. So if we subtract 2 from both sides, we're going to get a negative 2 cosine alpha cosine beta minus 2 sine alpha sine beta is equal to a negative 2 cosine of alpha minus beta. Now we're in the home stretch, divide everything by negative 2. Really, again, this is divide the entire side by negative 2, and then we're distributing. So this says that the cosine of alpha times the cosine of beta plus the sine alpha sine beta is going to be equal to cosine of alpha minus beta. So now we have the difference formula. All right, so Bugle, Kiwi Gamer Romania, and Reptept. Oh, Retrept. Have to read. Welcome to the stream. Okay, so if we want to look at this and say, well, we got to change some things, what we would like to do now is to be able to say what happens when beta is a, what happens when we want to add angles together. So if we want an cosine of alpha plus beta, no, that's not going to work. That's kind of a small space too. All right. Hey, hey. So if we want the cosine of alpha plus beta, we have to think about how this is related to what we just found. Well, if we were to say that this is the cosine of alpha minus negative beta, then all that's doing is saying we're just going to change from beta in the above ones to a negative beta, and then repeat the exact same formula that we had. So this is going to be the cosine of alpha times the cosine of negative beta plus the sine of alpha times the sine of negative beta. And if we think of things in terms of positive versus negative angles, if this is our beta here and this is our negative beta here, okay, if beta going up is x comma y, then beta going down, being negative beta, is going to still have the same x value. We're in the exact same location left and right, but now our y values are made negative. So if we wanted to look at the cosine of negative beta, this is going to be x over r, and it's the same x that we had up above for the cosine of beta. So nothing changed. If we want the sine of beta, that was y over r, compared to the sine of negative beta, well, it's our vertical distance. In this case, it's negative y divided by r. So then we compare it to what we had up here. Well, negative y over r is the same as negative y over r, so that's the same as negative sine of beta. Cosine of negative beta is x over r, which was the same as the original cosine of beta. Alright, so this forms what are called even and odd functions. Oh, sure. Which topic? I probably get about 10 or 15 minutes left on this next one formula, really. Not literally this one, just the next one. So if we do this, this is going to get us a cosine of alpha times, again, the same cosine of beta that we had before. Over here, however, the sine of negative beta becomes negative sine of beta times the sine of alpha. So this negative can kick out front and make it a minus sine alpha sine beta. So the cosine of alpha plus beta is going to be equal to cosine alpha cosine beta minus sine alpha sine beta. Yep, hey Salteds. So I'm doing just this because this is what I did in school or today, and I was waiting for people to come in. I also wanted to show the proof of the sine sum formula because I've never seen it before, and I figured it out, yesterday, and it's so easy. And I'm like, why did nobody ever show me this, or why didn't I even think to try this before? So, being a teacher, I was griping about it, saying, I don't know how to do this, and I'm really kind of frustrated that, there isn't a proof for it online somewhere, or at least not that I've seen. So I went and proved it and went, oh, well, that was easy. It was actually slightly disappointing. So the other way that people write this is that the cosine of alpha plus or minus beta is equal to the cosine of alpha times the cosine of beta. When you get a plus here, you get a minus here. When you get a minus here, you get a plus here. Sine alpha sine beta. So this is kind of the shorthand notation for how to write it. Hmm. I unfortunately don't have any necessarily good recommendations. The abstract algebra book that I used was pretty good, but then the question is it even still in print? Because that was a long time ago. So the one that I did was a first course in abstract algebra by John B. Fraley, F-R-A-L-E-I-G-H, I believe. Which I thought was good, but I mean, I was an undergrad, so I don't know if I'm the person exactly to ask about it. Best abstract algebra book for beginners I found from The Math Sorcerer. I'll link that in chat. So this is a video that goes into at least one, but come on. Yeah. So this guy, the Math Sorcerer, has generally speaking been pretty good. He also recommends Fraley. He also recommends Abstract Algebra, A First Course by Dan Saracino, Contemporary Abstract Algebra by Joseph P. Gallion, and Abstract Algebra by John Beachy and William Blair. So I'm not exactly sure. Again, I'm not exactly sure. I only ever did the Fraley book. I mean, like I said, I liked it enough, but I was an undergrad, so it's kind of in the middle of it. I don't know. All right. I am here. All right, so in order to figure out what the sine formula was for this, I was like, okay, what's the relationship I want here? Well, first of all, I want to turn a cosine into a sine. I need to get the sine of alpha plus minus beta. That's my goal. So the easiest way to do that was to work backwards and say that I need to then start with the cosine of, this is going to be pi over 2 minus parentheses alpha plus or minus beta. So use the cofunction identity that we talked about up above. So the cofunction identity says that any cofunction, when you take 90 degrees or pi over 2 radians minus the angle you started with, it's going to be the sine of that angle. And vice versa. Works the other way around as well. No, I mean, that makes perfect sense. Another section. Oh, man. There's another section of mathematics that I'm trying to think of. I don't know if it's topology, which maybe can work. Here, I'll look it up. This is something easy, and the internet knows. Yeah, so, group theory. So if you look into group theory, that's another one. You probably want to do abstract algebra first if you're doing that. But, yeah, looking at permutation groups and all that cool stuff. So yeah, writing out the mathematical notation for it, when you look at group theory, it makes a lot more sense. All right. Anyway. I said, okay, so starting with this, we're going to prove this a couple of ways. First of all, we're going to prove that the cosine of pi over 2 minus parentheses alpha plus minus beta, and break it apart and show what it is. Then I also said we're going to break this by associativity and associate the pi over 2 with just alpha. And then this minus gets distributed in and can make it a minus plus beta. And the only reason I'm caring about the fact that it's minus plus in this case is because when you negate something, the order is actually going to matter for this. So first of all, over here we break it up as it is on this subtraction. No problem. So we're going to do the cosine of pi over 2 times the cosine of alpha plus minus beta. This was a minus here, so we get a plus on the outside here. Then we get the sine of pi over 2 times the sine of parentheses alpha plus minus beta. When we do that, now we see that the cosine of pi over 2 is going to be 0. So this whole term is 0. The sine of pi over 2 is 1, and so this whole term here is just going to be the sine of alpha plus minus beta. Okay, then if we rearrange, reassociate, and then do the cosine formula based on this break, then this is going to get us the cosine of pi over 2 minus alpha times the cosine of beta. Since this is a minus plus for the cosine formula, we get a plus minus out there. And then we end up with a sine of pi over 2 minus alpha times the sine of beta. Cosine of pi over 2 minus alpha is the sine of alpha. We've already discussed that. Times the cosine of beta, plus or minus, sine of pi over 2 minus alpha is the cosine of alpha, times the sine of beta. So this is where you get the formula, sine of alpha times the cosine of beta, plus or minus cosine of alpha times the sine of beta. So I took one look at this once I got it, and I was just like, oh, yeah. Why didn't I do that, 20 years ago or whatever? That was pretty obvious. But at any rate, you do get this nice little formula here for both the sine and the cosine of alpha plus or minus beta. And now you can add and subtract your angles to your heart's content. One of my favorite facts from this, though, was the 15-degree angles, or your unsimplifiable multiples of pi over 12. So if we want 15 degrees, this is going to end up being, 45 minus 30. Or if I'm going to stay consistent for once, this is pi over 4 minus pi over 6. For the cosine formula, that's the cosine of pi over 4 times the cosine of pi over 6 plus sine of pi over 4 times sine of pi over 6. When we do all these out, we end up getting root 2 over 2 times cosine of this is root 3 over 2 plus root 2 over 2 times sine of pi over 6 is 1/2. So we end up getting the root 6 plus root 2 over 4 for the cosine of 1 pi over 12. And then if you wanted to do this for any other unsimplifiable multiple of 12 going all the way around the unit circle, then you end up doing the same stuff and you get the same numbers because you're adding and subtracting some version of pi over 4, pi over 6, or pi over 3 all the way around the entire unit circle. So the sine of pi over 12 can be left to as an exercise to the reader, is the square root of 6 minus the square root of 2 over 4. And basically all I think about when I'm doing this is it long or short? So are the root 6 and root 2 being added to make it long or subtracted to make it short? And is the overall result positive or negative, depending on what quadrant you're in? Interestingly enough, when you do the double angle formula for these, it ends up being a bit different. I guess it would be the half angle for what you all know. But I almost never memorize the half angle formula. I just happen to know it right now because I'm teaching it. But the half angle formula says that if you want the cosine of some angle theta, then you can take the square root. You know what? I'm going to go the other way. Absolute value of the cosine of theta is equal to the square root of 1 plus the cosine of 2 theta over 2. And the absolute value of the sine of theta is going to be equal to the square root of 1 minus cosine of 2 theta, over 2. So again, I'm repurposing the double angle formula and just solving for the other one. And you get a plus or a minus depending on what quadrant you're in. That's all that really matters. So if we're just doing pi over 12, then we don't need absolute values. We're just in quadrant 1. Both of them are going to be positive anyway. So the cosine of pi over 12 is going to be equal to a positive 1 plus the cosine of pi over 6, twice the angle of pi over 12. This is going to get us a square root of 1 plus cosine of pi over 6 is root 3 over 2 divided by 2. Multiply both top and bottom by 2. We end up getting 2 plus root 3 over 4, or the square root of 2 plus root 3, all divided by 2. And similarly for the sine of theta and sine of pi over 12, we end up with the square root of 1 minus. It's just the same number, so I'm not going to. And then multiply both top and bottom by 2. We end up with the square root of 2 minus root 3 all over 4, or the square root of 2 minus root 3 all divided by 2. And I looked at this, and I looked at the answers I had up here, and I was like, whoa, hang on a minute. Right, these do not look anything like these. We've got nested square roots down here, and you're telling me that these are the same as just the sum or difference of square roots up here? And the answer is yes. One of the things that you can do very easily is just to plug this in. Set them equal to each other. I'm not going to do it, but you're welcome to. My recommendation here is, if you want to actually prove this, move stuff on both sides. Don't try to make one become the other, because that's just kind of nasty. So yeah, like I said, if you end up with using the double angle formula instead of sum and difference formula, you get these things which look completely unalike. But well, that's good. But yeah, if you set these things equal to each other, you can actually prove that, 2 equals 2 or whatever, and show that they are the same. Yep. Back to the beginning. All right. So cosine comes first. What we do is we build out our alpha minus beta, which are going to be the angles between alpha and beta, wherever they are on the circle. Doesn't matter. Then we get the points for each of them: r cosine alpha, r sine alpha here, and r cosine beta, r sine beta here. We then take that entire triangle and just tilt it until the red line, formerly beta, aligns with the initial side. So now this point is at r comma 0, this point is at r cosine of alpha minus beta, and r sine of alpha minus beta for the other point. And since they have side, angle, side congruence with the other one up here, side, angle, side, they're congruent triangles, and therefore your d is labeled on both triangles is the same. Then find the distance formula. So d squared is going to be equal to your delta y squared plus your delta x squared for both of those. Again, they're going to be different numbers, but they're going to yield the same distance, d squared. When we write that down here, d squared equals delta x squared plus delta y squared, you then get all this nasty stuff here. So take your, what is that, delta x is your x1 minus x2, and x1 minus x2 on the other triangle. So we're just doing them on both triangles at the same time and setting them equal to each other. On the next line we say, okay, lose the d squared, keep the rest of it. Then all of these individual terms here that are color-coded are going to be a basic Pythagorean identity. Cosine squared of theta plus sine squared of theta equals 1. That should be a little bit over that way. Right? So this pair is equal to 1, this pair is equal to 1, and this pair is equal to 1. Technically it's equal to r squared, but we're going to also divide by r squared everywhere. This is what we get. We get a negative 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta equals negative 2 minus 2 cosine alpha minus beta. Subtract the 2's from both sides and divide everything by -2, and you get the basic cosine difference formula. If you want the sum formula, then basically all you do is change negative beta for beta, and then you get alpha plus beta. Then for the sine one, that was using the cofunction identity to say, okay, the cosine of pi over 2 minus parentheses alpha plus beta, plus or minus, we can do both, is equal to the sine of alpha plus or minus beta. That's our goal. We want that. So now we've got to manipulate the other side here on the left. Yeah, it's fine. You can catch it on the VOD. It's okay. Have you been up all night? And I do it to myself all the time. It's terrible. Okay. At least you got some sleep. It helps with the mathing. Okay. That doesn't help with the mathing. Yeah. Anyway, so yeah, that's the sine and cosine sum and difference formula. The doing the double angle formulas and then getting the half angle formulas are really easy from here, because to get the double angle you just say, okay, this is alpha plus, if you let beta equal alpha, alpha plus alpha, it's going to be 2 alpha. So sine of 2 alpha is going to be sine of alpha cosine of alpha plus or minus cosine of alpha. Well, it's only going to be plus because we're only going to do the top. Cosine alpha sine alpha, but that's just commutative multiplication, so put them together. Double angle formula is 2 sine alpha cosine alpha. And then if you look at the division or the subtraction, right? If it were alpha minus alpha, that's just the sine of 0, so you get 0. Yeah, I mean, it literally is nothing new. It's the sum formula, but you just let them be the same angle. Yeah, the only real thing that I like about it is if you're looking at something like, you know that the cosine of u is 7/12. Yes, I know that's not a Pythagorean triple, it's fine. If you know that the cosine of u is 7/12, then what is the cosine of u over 2 going to be equal to? Well, this is pretty easy. So you're going to go like this and say this is going to be 1 plus cosine of twice u over 2 is just u, so that's 7/12. So it's 1 plus 7/12 divided by 2. Again, this comes from the other formula. Cosine of u as a double angle is going to be equal to twice cosine squared of u over 2 minus 1. So just kind of rearrange everything, solve for this cosine here, and this is what you get there. So yeah, I kind of like some of this stuff anyway. I was like 20 years ago. Oh. Coming up on it. Looked at my wife. I was like, oh man, it's been 20 years. She's like, shut up. Nobody asked you. Which one? This stuff? Or, oh, math major. Right, yep. I mean, I liked it. I was also math education, rather than pure math. She was pure math, and she did a really great job with it. Um, she took topology, abstract and linear algebra. I forget what her top level courses were besides topology, but there were some good ones in there that I was like, man, I really wanted to take that. Oh, real and complex analysis, which I took as a part of my master's degree, like, you know, 5 years after. When you get into the real nitty gritty of it, yes, it's very hard, but just the basic principles of topology really aren't that bad. It's then when you have to formalize it that it's like, oh man. I tried working out of the book that she had, which I think is probably is it at school? No, it's there. Okay. Yep, she dual majored in math and theater and minored in psychology in 5 years. I don't deserve her. She's very awesome. Yes, so she originally wanted to be a psych major and took a bunch of classes with it, and then decided, you know what, this isn't good. I don't like this, and switched out from psych major. And then switched into math, and then she was like, this is really cool. I like math. And then at some point she was taking theater classes, and her advisor said, so look, you're only like one course away from a psych minor. And she's like, all right, cool, I'll take that. And then she also came across courses that she wanted to take in the theater department, and then they were like, you can't take those unless you're a major. She's like, that's stupid. Sign me up. So. So she has a BA in theater, a BS in mathematics, a minor in psychology, and an MS in computer science. So meanwhile, I barely got through my math education major, and then did MS in applied and computational mathematics, which had a lot of overlap with what I learned earlier. I'm like, yeah, it's kind of interesting. We do a lot of, or used to at least, do a lot of puzzle hunts. So we get a ton of puzzles and have to do sorts of stuff with them, and then go find new locations, and then do a puzzle there and find a new location. So we did a bunch of stuff like this, and we're much more evenly matched when it comes to like puzzles like that. She's still a lot smarter than I am in terms of that, but there are just some little things that click for me that don't for her, and I don't know what it is, but yeah, I did. Let's see. I need to get permission from my friend before I can actually share this. But I think I wanna do this on stream at some point. But since there are like 5 people who are ever gonna see this, this is a insane puzzle hunt that one of my friends created. You can just create like a fake account for it. It's fine. Put something on LastPass or whatever. Um, but there are 10 sections in which to solve all of the puzzles that are in each of these sections. And then all the nine. There are 9 rounds in which there are a number of puzzles to solve. Some of them are just like cryptograms, some of them are crossword puzzles, some of them are, there's a Sudoku that's all letters and stuff like that. Yeah. I've been working on this for years, and I'm gonna open this up and say, like, provided I get his permission, I'm gonna do this online, on stream with anybody who wants it, and then put like backseating welcome. Um, because this is kind of how we, like, this is how we do puzzle hunts, really. Like, the two of us is we'll sit down, we'll go through this whole thing, and then um, like, bounce ideas off of each other and stuff like that. Oh, that's, yeah, I mean, that's not mine. So he developed this when he was doing some programming job somewhere, and like he was done, and he went to the boss and he was like, "So what do I do?" And I need more work. And they're like, you could just wait for something to break. And he's like, that's okay, I guess. So he basically sat in a cube for 8 hours a day doing literally nothing and still getting paid. And he was like, okay, no, I can't do this. And some things broke occasionally, but it wasn't much. So he ended up making puzzles in his free time, and the boss didn't care. He was doing whatever he needed to get done still, whenever he needed to get it done. But he was basically being paid on retainer to fix anything that goes wrong. Sweet job if you can get it. But yeah, anyway, he built this puzzle hunt out. So each round is made up of a number of puzzles, and then once you get the answers to all of them, you take all of those answers and you go to the meta puzzle at the top. When you click the meta puzzle, it'll be obvious what you need to do with them. So you need to take those answers, mash them around, do a cryptogram, whatever, and then now you've got your new answer. You plug that in as your meta. Then all 9 rounds, you take the meta answers and you take all of them to the end. And the final puzzle takes all the meta answers from the 9 rounds and uses them in one puzzle. It's insane. I love it. I'm only done with like a quarter, maybe, of all the puzzles in the entire thing. I don't think I have any rounds actually done either. Yeah, and that's a good one too. I would like to, at some point, actually, like, probably make a textbook out of what I'm doing here, basically. All the things that I've learned over however many years teaching, make my own version, see what happens. We'll see. That takes a lot of time, and I don't know if I have that right now. All right. Did anybody want to see anything actually? There was another good. Yeah. I talked with this guy. His name's Harold Jacobs, and he came out with a book. Well, he came out with several books. Um, Geometry, seeing, doing, understanding. Um, and algebra, or elementary algebra. Oh, he's still alive. Awesome. Mathematics, a human endeavor. And what is algebra 1? Elementary algebra. Apparently new copies of elementary algebra are going for $140. I did not pay that. I think I bought it for $50. So that's interesting. I don't imagine that I've actually turned a profit on that. I think that's some weird. Huh. Weird. I got a few other people who are in the list, so welcome to Lurks, although that might be a bot, I just don't know. Ice Wizards and Casino Thanks. And Bugle, still see you in there. Now I see what you mean though. Yeah, when you see the number on it, it only says 1 or 2 or whatever. Yeah, they usually just toss you out once they figure out your card counting. Oh man, I'm going to be teaching this next semester coming up. I'm going to be teaching 2 new preps, although I've taught Calc 2 like long time ago. So I'm going to be teaching Calc 2 again, and then I'm going to be teaching it's like an intro class, intro to math for non-majors. You know, anybody who's interested in doing other stuff. They don't need calculus, they don't need pre-calc, they don't need college algebra even. It's like foundations in math. So they're going to be doing some probability, some set theory, like all sorts of cool stuff. And then I'm going to keep doing what I always do, which is bring in some historical context and tell them kind of, you know, that mathematics is not just some ancient scroll sort of thing. It's like, you know, it's not information passed down from on high. Yeah, I mean, it's basically what it had, or where it came from, or what came from it directly, and then kind of encompassed it. So my last week's thing of doing the Taylor series is going to come in handy at some point next semester. I love Taylor series so much. Yeah, there's pretty much 2 things that I learned growing up. You know, don't bother Oh, do you mean what's my setup? Oh, what got me? See, all I need to do is just read better. Um, I was originally sorry. It's one of the problems of having facial hair. Oh, okay. So I was originally a physics major, and I wanted to do theoretical astrophysics. That was like my thing. In fact, now that's in all my office. I have Hawking's Brief History of Time, The Universe in a Nutshell, um, Petition, huh? Yeah. Brief History of Time, Universe in a Nutshell, On the Shoulders of Giants. Um, and I've read the first two all the way through and understood most of it. Um, I really loved watching like all the specials that came on all the time. So, Neil deGrasse Tyson, Stephen Hawking, Phil Plait, like all these awesome. That's the other thing is I never really actually studied astronomy. I just studied astrophysics, and I never did any calculations. I just learned the like what it's all about. So when I was 17, I turned 17, and on my birthday, my dad got me a copy of A Brief History of Time, from Stephen Hawking, and inside of it were tickets to a place called the Wang Center in Boston, in Massachusetts, and it was probably 50 miles away from where we lived. So I mean, it's a good hike. It's an hour or two to get into Boston, and then to get back home from where we lived. And we went to this fancy French restaurant that was around the corner. Had escargot and a bunch of stuff. My dad is very metropolitan. We lived in rural New Hampshire. We ate basically meat and potatoes every night, and then we go off to this, we go off to some fancy restaurant, and I'm like, I don't know how to eat this. I was up for it though. That was kind of cool. Who would have thunk I'd eat slugs? So yeah, so we went into the theater. It was kind of, like a theater that you go to a play where you have a balcony, and we were sitting like way in the back, underneath in the mezzanine, and hmm. So we're sitting way in the back underneath the mezzanine, and I didn't actually mention what it was for, did I? Oh my god. I got tickets to go see Stephen Hawking at the Wang Center in Boston. Me and 1,000 of my closest friends. So, so my family packed up. We went to this French restaurant beforehand, and then we went out to go see Stephen Hawking. We sat in our seats, and he came out on stage in his wheelchair and had a prepared talk. And so basically, he just hit go, and then it went through pretty much the whole thing. He got to the end of the talk, and there was a question and answer portion. This was a lot harder because this was at the time when he still had some mobility, but mostly it was kind of squeeze oriented. So he had to like hold down or press and tap to move the cursor around the screen, and then eventually select individual words to form sentences. So he did have some prepared questions, but a lot of them he had to do kind of off the cuff, and it took 5 minutes maybe to answer any one given question. So they'd be like, here's the question, and Dr. Hawking would sit up there and uh, the person would say, okay, he's gonna go now, and then he'd sit there and tap away trying to answer, and the MC would be like, all right, give us about 5 minutes. And then everybody would just talk to each other. But it was kind of funny. It was the weekend after my 17th birthday, so like a day or two after my actual birthday. The local theater was playing some movie, and I was like, I'm gonna go see my first R-rated movie. Woohoo! Uh, Terrible movie. I mean, it wasn't awful, but not one of the best. My favorite mathematician, man, there's a lot of good ones. At that point, he still had the use of some of the muscles in his hands, which squeezed. He could squeeze, but barely, and so it was sometime not too long after that. Hi, Matthew. It was sometime after this talk that he was fitted with an ocular sensor, which would track his eyes movement to like anywhere on the screen. And then he could like blink or kind of squeeze his eye, and it would select something like that. All right, give me one sec. Yeah. So anyway, yeah, Hawking having Lou Gehrig's was like, why? And the doctors only gave him a few years to live after he was diagnosed at 20 something. 2022, he got diagnosed, and they were like, oh man, you've only got a few years to live. And then he lived until, what, 80? 50 years longer than he was supposed to live. He had a good life. He and his wife had a good relationship. They had great kids and all that, and he had a full life. It was really awesome. Well, and tenacity. He just refused to give up, was the other thing. So, yeah, I mean, alive these days, Lou Gehrig's attacks your muscles, yeah, and so it just causes your entire body to atrophy over time. Um, well, I mean, yeah, giving up was a choice or a consequence. I mean, see, that's the other thing, is that like Hawking could live his entire life in his head, right? Like all of the stuff that he was imagining, all of the like multi-dimensional mathematics he was doing in his head was allowing him to just keep working. Other people who didn't have that ability, didn't have that high, yeah, he had all of his senses otherwise. He had all of his faculties. But he could do multi-dimensional mathematics in his head, and then like talk with his grad students, and his grad students would copy things down. And there was a good one. He was giving a talk to a bunch of other grad students, and at that point he was a 30, and probably about my age, late 30s, early 40s, and he kind of went and he could still sort of talk. It was kind of like a and his grad students were entirely not just really good physicists, but they were also really good translators. So they got to know him. Some of them ended up, I don't know if they lived with him, but some of them got pretty close to that level at least. And and so they were working with him very closely, and he's giving a talk, and he kind of murmurs out an answer, and the grad student translates and then writes something down, and then he goes, what was that? Oh, he says that was supposed to be a 3, and he erases the 2 that he put on the board and puts a 3 or something like that. I mean, the whole room just kind of erupts in laughter, and Hawking gives a big smile. This was back in the 70s, maybe early 80s. Yeah, sorry about the depression. Um, I have managed to stay more or less unscathed in my life. At the very least, like, the problems that I had were temporary, and yeah, it was it was mostly just due to teenage angst. But hmm, well, and the problems that I had to deal with were not severe. So yeah, like if you lose time, you have to leave school or whatever. That's where it gets a little rough. Um, yeah, I was never medicated, fortunately. I mean, for me, but um, but hey, I'm glad you're here. Yeah, and if you need it, medication's great. I've got a lot of friends who have depression, and they're managing, they're keeping on top of it, and they're doing just fine. They're having great times. Mm. Yeah, and that's another thing. If you can find something you really enjoy and really want to do, everything else just kind of falls away for a little bit. Yeah, do you want to talk about it? I mean, let me know if it is actually your. Oh, oh man, that is a big question. Um, and actually, the stuff that I'm talking about, no, 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 this is good. Well, yeah, but he's like, why is that the case? Oh no, no, I got one for you. So what we learn in Trig. Actually, this is a good question. Where are you, Matthew? Where are you in your schooling, mathematics and otherwise? Because I want to get a gauge. I don't want to go too far into like my collegiate level parlance if you're like high school. And algebra 1. I imagine you're not algebra 1, but Oh, yeah, yeah. All right, no problem. So you've done this before. So when you get into, at least in my trig class, we get into talking about complex numbers as vectors. So like 5 comma 3 I, or 5 comma 3 could be representative of the number 5 plus 3I. Yeah, there's some really good stuff in abstract algebra. If you can, Kiwi Gamer and I were just talking actually about good. I mean, yes. That was where I was going with this. But anyway, we were talking about good books for abstract algebra. And John Fraley, Fraleigh, did one called, I had it, and then I probably got rid of that entire, I did, I got rid of that one. Fraley's A First Course in Abstract Algebra.
Hey everyone, in this video I want to go over 4 books.
Anyway. So we were looking at The Math Wizard. And he came up with a recommendation of 4 different books, as you probably just heard. Well, anyway, if you don't like this explanation, then we could probably just skip it. I mean, I wasn't going to say exactly it's just multiplying by 180 degrees, because, or rotating by 180 degrees, because there's a long time to... So it cancels out to 0 degrees. So the way that all of this works is that you've got your angle theta and your r value, which are then going to get you the r cis theta. And then when you multiply your angles, so r1 cis theta 1 times r2 cis theta 2, this actually goes back to what we were doing back here with the sum and difference formulas for cosines. Because if we write all this stuff out, which I know, I'm sorry. R1, R2, cosine theta 1 plus I sine theta 2, theta 1 times cosine theta 2 plus I sine theta 2. Right, when you FOIL all this stuff out, cosine theta 1, cosine theta 2, plus, this is going to be a minus I squared, it's minus sine theta 1, sine theta 2, plus I times the quantity. This is going to be sine theta 1, cosine theta 2, and plus cosine theta 1, sine theta 2. Okay, so all of this ends up becoming r1, r2 times cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So if you're talking anything with perfect real value, or perfect, anything with a real value only is going to be along the x-axis. Anything with a positive real value is going to be to the right. Anything with a negative real value is going to be to the left. So due to the fact that anytime you multiply two numbers together, you're going to add their angles. If you multiply two positive reals together, you're going to get 0 plus 0, which is then going to get you 0 degrees. If you then multiply two negatives together, that's 180 plus 180, which is going to get you 360. So now you're back in that way. Now you're back in the positive real direction. And a negative times a positive, that's a 0 plus a 180. So you're at nope, other one. You're at 180 degrees. Right. So when you multiply by a negative number, it adds 180 degrees to the angle that you just had. If you multiply by a positive, it adds 0, so it doesn't do anything. Yep. Right, so usually we talk about opposite numbers as just the number that has the opposite value. And so positives and negatives are opposite for each other in terms of real numbers. So if you're just thinking real numbers, then positive 1 and negative 1 are opposites, just because that's what we call opposites. But if you're talking about like complex numbers, you're probably thinking opposite in terms of like the complex conjugate, in which case you have a positive or negative real value, but then also a positive or negative complex or imaginary value. And the imaginary value being positive on one side, negative on the other, is going to tell you, maybe those are opposite. I think opposite, the problem with opposite is that it's an ill-defined term. It could depend on what the context is, right? It's not something that's technically mathematical. It's just something that we use in common parlance because we feel like using it. It's whatever it means in English. So this is also why inverse is kind of a sticking point for me in a number of different ways. So when you're talking about the inverse, my students do this all the time when we're doing pre-calc. They're like, oh, it's the inverse. Okay, which one? You've got 3 to pick from. Pick an inverse. And they're like, well, they're gonna like divide, right? And like, nope, that's not what we're doing. Right. So inverse is a mathematically, technically, like defined word. So inverse, you're talking about additive, multiplicative, or functional. Additive inverse, you have A plus A inverse. How do we do A inverse? Is it tilde? I mean, that's not A in set theory. I mean, a bar. Sure, why not? So A plus A bar is going to get you 0, which is the additive identity. So it's the thing that when you add to some number, you end up getting itself, right? Doesn't change anything. Multiplicative, you do the same thing. A times A inverse is going to get you 1, which is the multiplicative identity. Functional inverse is the thing that when you plug it into a particular function, you end up getting the functional identity back, which is a little weird, but it's x if you're talking about f of x as your original function. So that's off the screen. Right, so technically, if you want to get into a real interesting philosophical discussion about it, there is no such thing as division or subtraction. Right? All subtraction is adding some other additive inverse, or some additive inverse. When you do division, what you're doing is you're multiplying by some multiplicative inverse. Alright, so with respect to multiplication, you're saying that, like, -2 and +2 don't behave as opposites. Not just -1 and +1. Am I getting that? So take any integer a, and you're trying to multiply by something. What's your goal, I guess, is the other question, right? Yeah, and the 8-second lag isn't helping either, I'm sure. So I'm also on a math help Discord, which may help. I don't know that I'm actually allowed to, like, invite other people, but anyway, what's your goal here? So you're trying to multiply by some number and then get what? Yeah. So in terms of that, you're getting 0 when you add them together, which is the additive identity. Uh-huh. Yep. Right, because, I mean, you just turn subtraction into addition, and then it follows the same rules. But yeah, I get your point. Yep. I think I see where you're going with this. Yeah. So the way that I see it is that you're still breaking things. Oh, what was that? Okay. So you're still breaking things over 0. And the thing is that multiplication doesn't really care about 0 so much. So multiplication really much more cares about 1. So here you see that symmetry, although it ends up being a times 1 over a. And, right, when you multiply a small number by a small number, you end up with smaller numbers. And big numbers by big numbers, you get bigger numbers. So there's your symmetry, I think, is what you're going for. So I would say you again, you're trying to think of it, you are trying to think of it as breaking your numbers across 0, but multiplication doesn't really work with 0, right? Because multiplication by 0 is always 0, and multiplication of two numbers can never be 0 unless one of them was in the first place. But in this case, right, multiplication of two numbers equaling 1 shows you the inverse. Multiplication of two small numbers and two large numbers gets you things that are in those respective regions. So that's more where you're going, I think. So anything that's in here, a times b is less than a or b. And anything out here, a times b is going to be greater than either a or b. With respect to 0, again, because 0 is in the middle of a region. And then over here, you have to actually do absolute value of a times b. It's going to be greater than either magnitude. I guess technically that's the same for the middle here too. Ooh. Right, and that's kind of where I was going with the inverse thing up here, is that these inverses and these identities are different depending on what thing you're looking at. So again, my students look at additive inverse, multiplicative inverse, and functional inverse, and they just still say the word inverse, and I'm like, okay, but which one? Because these are three completely different things. Yes. Yeah. Yep, that might be a good analogy. Ironically, Kiwi and I were just talking about astrophysics beforehand. No, you came into some of that, but true. There is when they're added together, there is a net zero balance. So the energy that it took to create them is going to be the same as it releases to be destroyed. Whether that be like man-made energy, or whether that be 0-point energy. I mean, in a way, if a particle of matter and a particle of antimatter were created out of effectively nothingness, then it takes a great deal of energy to make that happen. So, again, in effect, your two particles now have a positive potential energy, and the overall yeah, they have positive potential energy, and the surrounding universe would have lost energy to have them created. So essentially, the universe has taken on negative energy. Right. So it takes energy to create mass from that perspective. Or there has to be some other elsewhere for it to come from. But we don't know of any elsewhere, so yeah. So I was talking with Kiwi earlier. I am fairly well read in astrophysics, which does mean that I understand at least some of the particle physics, and cosmology, and so that was my intended major first of all, but I ended up working on a project with all the rest of the physics majors, and they're like, we're all going to just be teachers, right? And then I was like, huh. Right, so they don't have the opposite in terms of mass. The condensed energy still has mass in both directions, but it has taken energy out of the field to create that mass. So the whole E equals mc squared thing. So let's say you have an infinite field of energy, right? If it's just flat and boring, then nothing's going to happen. But if there's some sort of like weird perturbation that happens, a collision with a different universe, something else random, there is the possibility that the energy can condense, or there is the possibility that energy will pop out of nothingness and create some stuff which then almost immediately get destroyed. So that's the 0 point energy that I was talking about. Yeah, I mean it's not super easy. You know, I have an intuitive understanding of it, but I don't have a mathematical understanding of it by any means. But if you start reading into, if you watch like, you know, BBC specials or PBS specials in America on astrophysics and all these cool things. Yeah. How'd that go? Possible.